for colligative properties. First of all, what are colligative properties? See, these are the properties which depend upon the number of particles, but not on their nature. Simply, colligative properties, the magnitude of a colligative property depends only on the number of particles, but not on what the substance is. Okay, only on the number. See, as such, co means together, ligare means bind, binding together. It actually covers the association part, which will be dealing in the colligative properties. Of course, there is association of the particles, there is dissociation of the particles. In some cases, there will be neither association nor dissociation. So, these are the two words from which the word colligative properties is derived. Now, what are the colligative properties? See, the colligative properties are the first one, relative lowering of vapor pressure or LVP. Better if we consider only this LVP, based on which we can explain two more. They are depression in freezing point. The other one is elevation in boiling point. Okay. These three are interrelated. And the fourth one, of course, is osmotic pressure. Okay. We've already discussed this lowering of vapor pressure and the relative lowering of vapor pressure things. Lowering of vapor pressure is nothing but P naught minus P. Relative lowering of vapor pressure can be given as P naught minus P by P naught. Now this LVP can be given as decrease in the vapor pressure of pure solvent when a non-volatile solute is added. Right. That is what we say lowering. Decrease in the vapor pressure of the pure solvent when some amount of a non-volatile solute is dissolved in it. Now we know that when vapor pressure decreases, obviously the boiling point increases, isn't it? Because it is very clear that boiling point and vapor pressure are inversely proportional. So when a non-volatile solute is dissolved, vapor pressure decreases, boiling point increases. because boiling point is nothing but the temperature at which vapor pressure of a liquid becomes equal to its atmospheric pressure. Becomes equal to atmospheric pressure. Now I can actually give you one more relation, even for this also. As I said, these three are related. You know, the freezing point and vapor pressure are directly proportional. See, boiling point can also be defined as the temperature at which the liquid and vapor phases are in equilibrium. Whereas here it is the temperature at which vapor pressure of the liquid and its freezing point, freezing temperature, or the solid form. Vapor and the solid form are in equilibrium with each other, right? Vapor and the liquid are in equilibrium at boiling point. Vapor and the solid form or the crystalline form are in equilibrium at freezing point. Now, just like the boiling point increases when vapor pressure decreases, in this case, we can give that when vapor pressure decreases, even the freezing point also decreases. So that is what is mentioned here. Depression in freezing. So these are all very clear. Lowering, nothing but the decrease in the vapor pressure of the pure solvent when a non-volatile solute is added to it. See, when vapor pressure decreases, boiling point increases. When vapor pressure decreases, freezing point decreases. So these three are very much interrelated. Look at these things. Okay. And even these are very important. Now let me give you two more very interesting. See, mathematically, it can be given as, see, the magnitude of any colligative property is directly proportional to the concentration of solute particles. Okay. Directly proportional to the concentration of solute particles. At the same time, it is inversely proportional to the molar mass of the solute. Of course, the first one is very clear because, as I said, the magnitude of the colligative property depends only on the number but not on the nature. Whereas the second one, we will come to know when we go for the colligative properties. Of course, we have already discussed one. Let us take the relative lowering of vapor pressure into consideration. We know that it is P naught minus P by. You can take P naught or P for a dilute or concentrated. This can be taken. And see, this is the relation. Come on. This, anyway, is inversely proportional to the molecular weight. If you consider the condensed form, it will become P naught, right? Now, then it will become the RLVP. but this is the condensed form of Raoult's law. Okay, so RLVP, which is a colligative property, has its magnitude inversely proportional to the molar mass of the solute. Okay, let us now go for the other colligative property, that is elevation in boiling point. Okay, it is represented by delta T. I'll give you details. Now, let me again say that when a non-volatile solute is added, to a volatile solvent, vapor pressure decreases, whereas boiling point increases. Vapor pressure, vapor pressure of the pure solvent P naught is greater than the vapor pressure of the solution. Okay, so in case of boiling point, it can be given as T, nothing but the boiling point of the solution. You can also say TB, boiling point of the solution is greater than the boiling point of the pure solvent, exactly opposite. Okay. Now this a difference, just like the difference of these two, that is P naught minus P, is called lowering of vapor pressure. In this case, the difference of these two, that is TB minus T naught B, is called delta TB. Now this of course can be given as delta VP. I mean difference in the vapor pressure. Just like that, here it is delta TB. Okay. The same can be graphically shown by taking vapor pressure on y-axis and temperature on x-axis. Now, we know that the vapor pressure does not increase linearly with the temperature. It increases exponentially until the critical temperature of the liquid is reached. Okay. Now, say this is the vapor pressure. I mean, this is regarding the pure solvent. Okay. Let this be the boiling point of the pure solvent, P naught B. See, this actually gives the vapor pressure of the pure solvent. Okay. Now, when a non-volatile solute is added to it, what happens is, you get this. So this is for a solution. Vapor pressure of the solution. Let me just take it this way. Okay, proper. Because we know that the vapor pressure of the solution is less. So let this be P naught and this be P, right? Now this is the atmospheric pressure. This is a difference. See, P naught is greater than P. Whereas if you consider this portion, you will get the boiling point of the solution. This is solution curve. We have given all the details properly. Now from this, we can give it as TB is greater than T naught B. So this is, of course, delta TB. Very clear from the graph. We have proved everything. Vapor pressure of the solvent is more, solution is less. Very clear from these 2 points. You can check out. Now, when you go for this area, this is the boiling point of the solvent. I mean, this is the temperature at which the vapor pressure of the solvent, the vapor pressure of the solvent has become equal to atmospheric pressure. So is the boiling point of the pure solvent, right? Now look at this. This is the temperature at which boiling point of the solution, vapor pressure of the solution has become equal to atmospheric pressure. So everything is very clear, right? Now, see, it was experimentally proved that the elevation in boiling point is directly proportional to molality of the solution. Okay. So this can be written as delta TB is equal to KB into small m. This KB can be given as molal elevation constant or boiling point elevation constant or specifically ebullioscopic constant. Okay. So this constant, of course, is a specific for a solvent. Let me give you an example. See, for water, it can be given as 0.52 Kelvin kg per mole. Okay. 0.52. Okay. That way, it is different for different solvents. This Kb can be given as R T naught B square by 1000 into LV, where this R refers to gas constant, T naught B is anyway the boiling point of the pure solvent, and this LV is the latent heat of vaporization. See, this is per gram of solvent, remember. Per gram. So if you want this in per mole, you can actually take it this way. T naught B square by 1000 into delta HV by M. Of course, M dash, because we generally use M dash for the solvent. Now this delta HV is the molar heat of vaporization or enthalpy of vaporization per mole. Okay, so that is kV. Then how do we define this? Considering this expression, see in the expression delta TB is equal to KB into small m. When small m is equal to 1, I mean when molality of the solution is 1, that means when 1 mole of a solute is present in 1 kg of the solvent, then obviously delta TB becomes equal to KB. So now let us define this. Elevation in boiling point. Elevation in boiling point that is produced when molality of the solution is 1. Okay. Now, let us go for the final expression, taking the same thing again. Delta TB is equal to KB into small m. And we know that molality is a weight of solute by molecular weight of solute into 1000 by weight of the solvent in gram. Okay. So from this, we can derive the expression for the molecular weight of the solute, which is what is intended, which is what we are going for all the colligative properties. So M dash can be given as KB into small w into 1000 by delta TB into capital W. See, this is when KB is given for 1000 gram of the solvent. Sometimes they give it per 100 gram of the solvent. In that case, the same can be modified as KB into small w into 100 by delta TB into capital W. This is when KB is given per 100 gram of solvent. Okay. So these are the important relations. This is how we can also prove that delta TB, I mean, the elevation in boiling point is inversely proportional to the molecular weight of solute. Okay.